I was asked to give a brief introduction into the topic of IT in energy systems or broader smart grids and sprinkle a little bit of what we are doing or what research and development in Germany is currently doing on that front. And I broadly termed this introductory presentation ICT-based renewable energies integration and testing. Because testing, it was just mentioned already, is a huge aspect and a huge challenge when we are talking about new technologies such as blockchain, such as cloud and everything that we are currently introducing into our energy system, into our critical infrastructure, which is used to be tested very thoroughly before we put it into action, before we switch it on basically. And now we have all these technologies that, well, aren't just tested this way, and the question is how can we actually proceed in this, and what can we actually do about this? So, at some point, yeah. So that's the title of my presentation. I'd like to start up with, and typically start up with reminding ourselves what kind of system we are dealing with. Because typically when we talk about ICT systems, yes, we're talking about the internet, which is a large system, and some people try to compare it with the energy system, but that's totally wrong, because the power system itself has a lot of characteristics that are pretty unique and pretty complex and hard in its own, and make it a really complex system to be controlled and run and optimized by such a system. First, it's a critical infrastructure. It must not fail. If it fails, we are all very much subjected by this, and it hurts. Obviously not true for the internet, even though we feel hurt if we cannot use the internet for a prolonged period of time, but that's a phantom pain I would call it, comparing it to failures of a critical infrastructure. It is really huge from a European perspective. We always say Africa to Scandinavia, Ireland to Asia, and that from a European perspective is immense. We know now that India, or not just now, India from a diameter perspective is even larger system, so that's quite a large, you could say a cyber-physical system to control and govern to, and a lot of challenge involved in this. The propagation of phenomena and the dynamics is just fast, so basically the velocity of the electromagnetic wave through the medium copper through a cable is the velocity with phenomena that we have to deal with. That's also something that you cannot see in transportation systems or so, where, well, events propagate with the maximum speed a vehicle has or something. That's just not here. We see events propagate really fast in a dynamic system, and again, that's really unique. And we have an omnipresent conflict of objectives. In Europe maybe more so than in India, with a lot of unbundled liberalized stakeholders trying to compete with each other. Those are individual objectives that need to be ordered out in a way that is stable and efficient to the system. That's a challenge on its own. Well, and that's undergoing a rapid and fundamental change. So, of course, we are talking about renewable energy systems with a lot of, forecast, that are prone to forecast errors. Small size systems that in large numbers are system critical as a whole. Today, this morning, we learned about forecasting of these systems. We are networking them through digitalization. So on the power system level, they are already interconnected, but now we're introducing a complete new level of interconnectedness that introduces new dynamics that spill back over to the primary power system. And that's something that we have to observe very closely. And again, we are introducing new competition and business models. We are talking about new products also this morning. And again, we are introducing even more competition in the system that's actually reliant on running smoothly and not having too many objectives collide with each other. Yeah, and then we're introducing a lot of digitization trends. And during lunch, we talked about blockchain. We have one paper of blockchain here. We're talking about cloud, outsourcing, running power system operation in data centers elsewhere, and so on. So those are a lot of technologies that are pushing into the system, that are willingly accepted because, as we just heard, data is the new goal. We need to process this, we need to monitor, we need to aggregate this, but we must not forget this is a domain or technology that runs under completely different reliability standards than the power system that we are used to. So we are used to installing systems, running ICT systems that are patched every week. Every morning I look at the App Store, see what kind of security updates are available for my apps. So that's the world that we're living in the ICT sector, which is completely different from the power system. But now we're introducing both and we are combining both. So that's a challenge on its own because we are getting a lot of, or we're transporting a lot of these effects from the IT domain now into the power domain. Those are a classic, I would say, IT challenges. We have to deal with much more errors, much more failures of the system. We have to deal with updates concurrently. We have to talk about cybersecurity. And this is just a few of them. Now, if we look at what we typically understand, or the things that we understand under the term smart grid, that's a lot. And I'm not going through all of this, so there are a lot of functions. We're talking about network monitoring, forecasting of not only generation, but also of utilization. We have a lot of monitoring, state estimation, automation, control. We have demand-side management, virtual power plants, sector coupling, things that we are going to hear later in the session as well. But that just means, given what I just said, that we're introducing a wide range of these error sources or these entry points into a safety critical infrastructure. And again, the question is, how do we test these things? And every one of you who knows how testing typically works, you take a component, put it in a test setup, in a test environment, and run tests, predefined tests. And in the end, if not completing and not failing for the couple of tests, you have a tested system and you're certified. That's obviously not working anymore with systems that act drastically different once they're installed, because there's not just one system of it available, but a number of systems. And the system itself could be a controller, runs dynamically with the other controller and reacts to this dynamically. If you have two, you can plausibly think about this. If you have 1,000, it becomes difficult, but we're talking about systems with millions, hundreds of millions of these components. And the question again is, what are the systematic effects and how can you do this? At OFFIS, which is an ICT institute, I'm a computer scientist. I did my PhD in electrical engineering in Dortmund. We not only do a lot of research on all of these topics, but we also develop test methods. And one thing that we are doing for a couple of years is AI-based testing. So basically on installed systems that we use in these complex interconnected setups, we are trying to analyze and investigate and identify critical scenarios and situations that are relevant to the overall performance of the system and generate not only test cases out of this, but also strategies, mitigation strategies for these kinds of things. And how do we do this? Typically, we have this kind of setup. Those are, typically neural networks, deep learning, you could call them these days. And we have an artificial intelligence neural network that probes the system and tries to find scenario setups where you excite the system to such a state that becomes dynamically unstable or that is somehow interesting in a context of the tester. We typically couple this with a so-called defender agent who now tries to mitigate the situation, but also learns mitigation strategies and so on and so forth. This goes forth and back, and obviously the system in the middle is then a component, laboratory setup, or even a large-scale simulation of the system that you're actually interested in, and under investigation. And that is very interesting in terms of testing, and I'm going to show you a couple of results in just a few minutes. Yeah, what can you do with these kinds of setup? And as I said, this is, I would not call it a trend, but actually it's now subject to a couple of projects currently in Germany trying to come up with test methods, maturity models for these kinds of interconnected systems. Actually use these kinds of techniques to come up with new relevant test cases and not rely on the classic test cases, the static test cases that might not be relevant anymore because context is missing or was missing when these test cases have been developed. Well, then you can use only the one side, the attacker, to actually explore the system, to do it basically in a laboratory setup, and explore the vulnerabilities of the system, record this, and basically assess the system in terms of that. You can train the defender with it and basically come up with a controller that directly mitigates, for example, dynamic oscillations or negative effects when you have these components in place. And it's important to say that even though we talk about attackers and defenders, that's basically because this is kind of a game theoretic setup that's they're used. We're not talking per se about malicious attacks, but because we're talking about forecast deviations, damage caused by accidents, or even dynamic interactions. We had a large-scale project for some DSOs a couple of months back where we tested controller interactions. So we have tap changers on a transformer, we have voltage control at inverters, and maybe some dynamic scheduling controllers in the middle. It was interesting because the hypothesis was that those interact with each other and see the scenarios where they interact. For example, the tap changer taps up and the inverter controls against this. At some point, you are at the borders of the control range, and then you can't do anything anymore. And of course, the interaction patterns here are much more complex. But the thing is, using these kinds of techniques, you can identify, or not only identify these scenarios, but also come up with mitigation mechanisms, so controller settings, to actually work around this. Yeah, dynamic interactions, you can also use this. I'm now switching to cyber attacks because cyber attacks are much more fascinating topics, even though it's always important to know that those are very critical, malicious attacks. But again, this is also a technique that can be very well used to come up with these incidents. And this is something that we're now doing for 1.5 years, roughly, using these AI-based testing to come up with, to identify cyber attacks and also mitigation strategies here. And the example that you're about to see now is we're seeing a system where we have an attacker agent that uses some parts of the system here, the right side, and attacks the system, tries to deteriorate the performance of the system. Then we have the defender using his means, his actors, and so on to do something against this. The defender broadens his attack base because he's able to control other devices from the point of entry that he's using, and so on and so forth. And it goes on and back, and at some point, either the attacker or the defender reaches a state that's, well, stable or not. And that's something that's quite successful in these couple of projects. We also do with industry partners now to test their systems. And just to give you an impression how this actually looks, this doesn't look good. That's protected, it's IP protected. So okay. The first one was actually a much more basic scenario, but it was basically looked a little bit or similar like this. You have the attacker, you have the defender. This is already now a system from a European distribution system operator, which is now well scrutinized by this attacker agent, and we are also trying and training defender agents that are then coming up or controlling against these strategies that typically are targeted to excite some synchronization behavior, for example, electric vehicles, distributed generation, turning them on and off or ramping them up and down to reach a critical mass and trigger protection systems. So that's a classic learnable tactic from an attacker agent that is typically quite successful, and then the defender agent tries to come up with means and mechanisms to actually defend this. What you're seeing here are basically the channels, the control channels that either side has to actually well influence the system or do something against this. Yeah, you can do this for a wide range of setups. As I said, you can use it for single devices, you can use interactive systems and so on. Yeah, that's what we're doing. Yeah, basically what I just said is these AI-based testing schemes are a way to find these dynamic interactions and test systems as a whole in context. We're also now using them for also system planning and testing, because nowadays typically budget-based testing is on risk mitigation, and here it's basically reaching an equilibrium state and not trying to prevent everything from being happening, but basically trying to come up with a compromise and see what is actually, what can happen and how stable could that actually be. And one important message to lead over to this session is there's no way back from digitalized energy systems, because typically people like to ask, with all that you're just saying, introducing negative interactions, cybersecurity incidents, why don't we just don't do it? So don't use digitalization, don't go to IT-based systems. The thing is that we are way past this point of no return. We are already using forecast systems, we have SCADA systems, we rely on data acquisition and so on. So there's no way of turning this back, but we now have to find a way to actually make this stable, make this tested, make this more secure, and it's important to stress this and not trying to follow this unfulfillable dream of rolling things back to a time which honestly never existed. Yeah, and without further ado, I'd like to hand back over to the rest of the session. Thank you very much.